In 2016, two astronomers at Caltech published a paper that sent a shockwave through planetary science. They had noticed something strange happening at the far edge of our solar system, a pattern in the orbits of 6 icy objects that all seemed to be tilted the same way, as if something massive and completely invisible was quietly tugging on them from the darkness beyond Neptune. At first, the explanation seemed obvious. There had to be a hidden planet out there, something bigger than Earth, orbiting so far away it would take thousands of years to complete a single trip around the Sun. Astronomers named it before they had even found it, Planet 9, but nearly a decade later, after scanning enormous swaths of sky with some of the most powerful telescopes on the planet, nobody has found it. Not a single confirmed image, not one direct detection. And that failure has pushed a handful of physicists toward an idea that sounds like it belongs in science fiction. What if the thing bending those orbits isn't a planet at all? What if it's a black hole, sitting quietly inside our own solar system, closer to Earth than the nearest star, and small enough that you could hold its event horizon in the palm of your hand? If questions like this keep you up at night, you're in the right place. Hit subscribe now, because we dig into the biggest unanswered mysteries about our solar system and the search for habitable worlds every single week. And this might be one of the strangest ones we have ever covered. All right, let's get back into it. To understand how astronomers went from a single measurement to floating the idea of an invisible black hole, you have to go back further than 2016. The very first hint that something was off came in 2003, when astronomers discovered a small icy world called Sedna. Sedna's orbit was strange from the moment it was found. Instead of following a relatively normal path around the Sun, it swung out to an almost unbelievable distance, more than 86 billion miles at its farthest point, on an orbit so long it takes over 11,000 years to complete just one full loop. Nothing should have been able to push Sedna's orbit that far out, using only the gravity of the planets we already know about. For years, astronomers treated it as an interesting outlier and moved on. Then in 2014, a second object turned up with an almost identical kind of orbit, nicknamed 2012 VP113. And that's when a small group of researchers realized they might not be looking at two flukes. They might be looking at the beginning of a pattern. Beyond Neptune, in a region called the Kuiper Belt, there are thousands of icy bodies left over from the formation of the solar system. Most of them orbit the Sun in every direction imaginable, scattered across the sky the way you would expect debris to settle after 4.5 billion years. But Sedna and 2012 VP113 were only the beginning. Konstantin Batygin and Mike Brown, the two Caltech scientists behind the 2016 paper, went looking for more objects with that same strange alignment, and they found them. 6 of the most distant known bodies in the solar system were clustered together, all pointing in roughly the same direction, all tilted at a similar angle, like they were being herded by something with real gravitational muscle. When the pair ran the numbers, they calculated that the odds of this happening by pure chance were incredibly low, somewhere around 1 in several thousand. And when they modeled what kind of object could cause that kind of alignment, the answer came back consistent every time. Something with roughly 5 to 10 times the mass of Earth, sitting somewhere between 400 and 800 times farther from the Sun than we are, exerting just enough gravitational pull to line up 6 distant worlds without anyone ever directly seeing it. The specific measurement they were looking at is called the argument of perihelion, which basically describes the angle at which an object's orbit tilts relative to the rest of the solar system. Left alone, that angle should drift randomly over millions of years, the same way a spinning coin eventually lands in every possible position if you flip it enough times. Instead, objects like Sedna, 2012 VP113, and several others including 2004, VN112, and 2013 RF98 were all sitting near the same narrow slice of angles, as if an invisible hand kept nudging them back into formation every time they tried to drift away. That kind of persistent order doesn't happen by accident in a system as old and as chaotic as ours. This would not be the first time astronomers found a planet by watching what its gravity was doing before ever seeing it directly. In the mid-1800s, astronomers noticed that Uranus wasn't following the orbit predicted by Newtonian physics. Something was tugging on it. A French mathematician named Urbain Le Verrier calculated exactly where an unseen planet would have to be to cause that exact kind of wobble. And in 1846, astronomers pointed a telescope at that precise spot in the sky and found Neptune within about 1 degree of where the math said it should be. It remains one of the greatest triumphs of mathematical prediction in the history of science. Planet 9 was supposed to be the sequel. Same method, same logic, a slightly bigger telescope. Except this time, after nearly a decade of searching, the sequel hasn't delivered. So the hunt began in earnest. Teams around the world pointed some of the most sensitive instruments ever built at the patch of sky where this planet should be hiding. The Dark Energy camera in Chile, built originally to study the expansion of the universe, got repurposed to scan for it. The Subaru telescope in Hawaii, with one of the widest fields of view of any major observatory, spent years sweeping the same region. Pan-STARRS combed through years of archived sky images, looking for anything that moved the way a distant planet should move. And every single search came back empty. Not because the searches were sloppy. These are some of the best astronomers and the best equipment on Earth. The problem is scale. If Planet 9 exists, it is so far away and reflects so little sunlight that even a world several times the size of Earth would appear fainter than almost anything else we have ever tried to photograph. Finding it would be like trying to spot a single grain of black sand on a beach at midnight, using nothing but the faint glow of starlight. That is when, in 2019, two physicists named Jakob Schultz and James Unwin looked at the same data everyone else had been staring at and asked a completely different question. What if we have been searching for the wrong kind of object this whole time? They pointed out that every gravitational signature Badajian and Brown had found, the exact same clustering of orbits, the exact same pull on those 6 distant objects could be produced by something that weighed the same as the predicted planet, but took up almost no space at all. Not a planet, a black hole, and not the kind most people picture when they hear that phrase. Most black holes we know about form when a massive star runs out of fuel and collapses under its own gravity, crushing itself down into an object so dense that not even light can escape it. Those are stellar black holes, and they are usually many times the mass of our sun. But Schultz and Unwin were not talking about that kind. They were talking about something called a primordial black hole, a theoretical type of object that would have formed in the first fraction of a second after the Big Bang, long before any stars existed. In that first instant, the universe was an incredibly dense, chaotic soup of energy. Physicists have long suspected that in certain pockets, the density spikes so high that regions of space collapse directly into black holes without ever going through the star stage at all. These primordial black holes could theoretically come in almost any size, from something lighter than an asteroid to something rivaling the mass of a planet. And if one of them happened to be drifting through the galaxy with roughly 5 to 10 times the mass of Earth, it would fit the exact gravitational profile astronomers had already calculated for Planet 9. There is also a reasonable explanation for how a wandering black hole could have ended up trapped in our solar system in the first place. Stars are almost never born alone. The sun likely formed inside a dense cluster of thousands of other young stars, all packed closely together for the first several million years of the solar system's existence. In an environment that crowded, a slow-moving primordial black hole passing through would have had a real chance of being gravitationally captured, tugged into a wide, stable orbit around the sun before the birth cluster eventually dispersed and drifted apart, the way most stellar nurseries do. If that happened here, the black hole would not be a recent visitor. It would have been quietly orbiting the sun, farther out than every planet we know, for 4.5 billion years. Here's the part that tends to break people's brains a little. A black hole with 5 to 10 times the mass of Earth would not be some sprawling cosmic monster. Its event horizon, the boundary past which nothing can escape, would only be about 4 to 9 centimeters across. That is roughly the size of a grapefruit or a bowling ball. You could crush the entire mass of Earth's slightly bigger cousin down into something you could physically hold, and it would still exert exactly the same gravitational pull on everything around it as a full-size planet would from that same distance. Gravity doesn't care how spread out or how compressed an object is. It only cares about mass and distance. So from 400 astronomical units away, a black hole the size of a grapefruit and a planet the size of Neptune would look, gravitationally speaking, completely identical. The only difference is that one of them reflects sunlight and the other one reflects nothing at all. And this is where the story stops being about one missing planet and starts becoming something much bigger. Primordial black holes are not just a convenient explanation for a handful of strange orbits. Physicists have been chasing them for a completely different reason for decades. They are one of the leading candidates for dark matter, the invisible substance that makes up roughly 85% of all the matter in the universe and that we have never been able to directly detect. If a primordial black hole really is sitting in our own solar system, it would not just solve the Planet 9 mystery. It would be the first direct evidence that these objects exist at all, and it could open the door to understanding what most of the universe is actually made of. Interest in primordial black holes as a dark matter candidate got a serious boost in 2015, when the LIGO detector picked up the first ever direct observation of gravitational waves produced by two black holes merging together far across the universe. Some of the black holes LIGO has detected since then have masses that do not fit neatly into the models astronomers use to predict what stellar collapse should produce. That mismatch reopened an old question. What if not every black hole in the universe came from a dying star? What if some of them have been here since almost the very beginning? That is the reason this idea, strange as it sounds, has not been laughed out of the room. It is not just a fringe theory chasing an oddity in the Kuiper Belt. It is a shot at answering one of the biggest open questions in all of physics, using data we already had sitting in our own backyard. So how do you even go about hunting for something you cannot see, that doesn't emit light, and that is smaller than a beach ball? Physicists have come up with a handful of clever approaches. The first is gravitational microlensing. Einstein's theory of general relativity tells us that any massive object bends the light passing near it, and a black hole drifting in front of a distant star, even briefly, would cause that star's light to flicker and brighten in a very specific, very recognizable way. If a primordial black hole is out past Neptune, slowly moving against the backdrop of far more distant stars, it should eventually pass in front of one of them and produce exactly that kind of flash. The second method involves waiting for it to eat something. Black holes are not perfectly quiet even out in the emptiness of the outer solar system. Every so often, a stray comet, an icy fragment from the Oort cloud, or even a wisp of interstellar dust could wander close enough to get pulled in and torn apart before crossing the event horizon. That process, called accretion, releases a burst of energy, sometimes in the form of a faint flare of light, sometimes in X-rays or gamma rays. Astronomers Amir Siraj and Avi Loeb at Harvard proposed that if we watch the right patch of sky for long enough, we might eventually catch one of these flares, a brief cosmic hiccup marking the exact moment something met its end. The problem is that these flares would likely be incredibly faint and incredibly rare, which is exactly why nobody has caught one yet, and exactly why survey telescopes built to stare patiently for years, rather than take one quick snapshot, matter so much. Some researchers have already started combing through years of archived data from the Fermi Gamma Ray Space Telescope, looking for any unexplained burst that lines up with the region of sky where Planet 9 is predicted to be, on the chance that a flare was captured years ago and simply never connected to this particular mystery. And there is a third, quieter method. Spacecraft. Every probe we have ever sent past the outer solar system, from Cassini around Saturn to New Horizons past Pluto, has its trajectory tracked with extraordinary precision, down to fractions of a meter. If something as massive as a black hole is tugging on the outer solar system, it should leave a tiny measurable fingerprint on those trajectories too. A gravitational nudge too small to see with the naked eye, but not too small for the instruments already on board our own spacecraft. Some researchers have even proposed combing back through decades of archived tracking data from missions that flew through the outer solar system years ago, hunting for that fingerprint retroactively in data that has been sitting in storage the entire time. For most of the last decade, all three of these methods have shared the same problem. None of our telescopes were built to stare at the same patch of sky, night after night, for years on end, patiently waiting for a single flicker that might never come. That changed with the Vera C. Rubin Observatory in Chile, which achieved first light in 2025. Its remote mountaintop site high in the Chilean Andes was chosen for its really dark, stable skies. Rubin is not a typical telescope. It is built around the largest digital camera ever constructed for astronomy, and its entire mission, called the Legacy Survey of Space and Time, is to photograph the same swath of the southern sky over and over again for 10 straight years, cataloging every single change it can detect. The observatory's camera alone is roughly the size of a small car and produces images so detailed that a single one would need hundreds of ultra-high definition television screens to display at full resolution. Every clear night, it will generate roughly 20 terabytes of new data, more information in a single evening than most previous sky surveys collected in years. For a hidden planet, that means an extraordinary chance of catching it reflecting sunlight where nothing was expected to be. And for a primordial black hole, it means something even more interesting. A 10-year survey scanning billions of stars repeatedly is exactly the kind of instrument that could catch a micro-lensing flicker or an accretion flare that any shorter survey would have completely missed. If there really is something dark and massive drifting through our solar system, Rubin might be the first telescope in history actually built to notice it blink. Now, not everyone in the astronomy community is convinced that either explanation is correct. Some researchers, including teams working on the Outer Solar System Origins Survey, have argued that the clustering Badagen and Brown found might not be a real physical effect at all. It could simply be a bias built into how these objects get discovered in the first place. Surveys tend to scan certain parts of the sky more thoroughly than others, which can make objects look artificially clustered, even when their true distribution is closer to random. Other physicists have proposed that the pull we are seeing could come from the combined gravity of a much larger, much fainter population of smaller Kuiper Belt objects we simply haven't detected yet, rather than one single massive body. And a few have gone even further, suggesting the anomaly might hint at something wrong with our understanding of gravity itself at extreme distances, rather than pointing to a hidden object at all. Even Mike Brown, one of the two scientists who first proposed Planet 9, has been careful to say that the black hole idea, while mathematically consistent with the data, remains the less likely of the two explanations. Most astronomers still think a genuine, if unusually distant planet is the more probable answer. But probability is not proof, and until something is actually detected, every explanation stays technically on the table. So why does any of this matter beyond satisfying scientific curiosity? Because understanding the true architecture of our own solar system is not just about filling in a gap on a map. Every planet, moon, and icy world capable of supporting life depends on a delicate, long-term gravitational balance, one that keeps orbits stable over billions of years, instead of chaotic and collision-prone. If there is a massive, invisible object quietly influencing that balance from the outer dark, we need to know what it is and how it behaves. Because the same physics that shapes the outer solar system today shaped the environment life on Earth was allowed to evolve in for 4.5 billion years. A solar system is not a static picture. It is a slow, ongoing negotiation between every object massive enough to matter. And we may have been missing one of the biggest players at the table this entire time. Astronomers studying planets around other stars already know that a system's long-term stability depends heavily on the arrangement of its biggest objects, especially the ones far from the central star that most instruments can barely see. When we point telescopes like the James Webb Space Telescope at other solar systems searching for a habitable world, we are making assumptions about what a typical, gravitationally stable system looks like, based largely on our own. If our own backyard turns out to be hiding a 5 Earth-mass black hole that has gone unnoticed for the entire history of astronomy, it raises an uncomfortable question about what else might be hiding in every other system we are currently studying, quietly influencing which planets get to stay in stable, life-friendly orbits and which ones get flung into the dark. There is a bigger implication too. If primordial black holes really do exist and really can drift through planetary systems undetected, that changes how we think about young solar systems everywhere, including the ones we are now scanning for signs of life around other stars. A rogue black hole passing close enough to a forming planetary system could scatter icy bodies, disrupt fragile orbits, or even seed a young system with organic material carried in on the debris it perturbs. Suddenly, the search for habitable worlds is not just about finding the right kind of star or the right distance from it. It is about accounting for every invisible force that could be quietly rearranging the furniture long before a single planet ever finishes forming. As of right now, nobody has confirmed either explanation. Planet 9 could still turn out to be exactly what it sounds like. A large, cold, ordinary world simply waiting for the right telescope to catch it in the right patch of sky. Or it could turn out to be something far stranger, a leftover fragment of the earliest moments of the universe, drifting silently through our own cosmic backyard for billions of years without a single person on Earth ever knowing it was there. The Rubin Observatory's 10-year survey is not scheduled to wrap up until the mid-2030s, which means the earliest complete answer to this question might still be years away. But partial results start rolling in almost immediately, and every one of those early data releases will be scoured by physicists, checking one thing first: whether anything in that sea of new images flickered the way a black hole should. Either way, the fact that we cannot yet rule out a black hole quietly orbiting less than a light year from our own front porch says something remarkable about how much of our own solar system remains completely unmapped. We have sent spacecraft to touch the surface of the sun and land on comets millions of miles from home. And there might still be an object with the mass of several Earths hiding in our own gravitational backyard that we have never once laid eyes on. Somewhere out past Pluto, something has been quietly writing its signature across our most distant neighbors, and we are only now learning how to read it. For now, the mystery stays exactly where it started, tucked into 6 sets of numbers describing orbits nobody can fully explain. But somewhere in Chile, a camera the size of a car is already watching the dark, and on the right clear night, years from now, it might still catch the flicker that tells us the whole truth once and for all.